So this is going to be a recap of our learning task 8.2 square root concepts, starting with slide 16. And here we have 2 times the square root of 3 times the square root of 3. There's a couple ways to think about this. One way is we can condense the 2 square roots into one, and so we could think of it as 2 times the square root, and underneath that is 3 times 3. And we know that 3 times 3 is 9, so we could write it as 2 times the square root of 9. Another item you could have recognized is we had 2 radicals that were the same being multiplied together. So that's like the square root of 3 squared. Square rooting and squaring are inverse operations. They undo each other. So if you recognize that, we know that now we just have 2 times 3. And 2 times 3 is equal to 6. So we could have written 6 or 2 square roots of 9 for right now for our slide 16. As we go to slide 17, notice how we have items on the exterior of the radical that interact with each other. So we've got 2 times 3. We have 2 radicals here, so the interiors can interact with each other. So we've got underneath this radical 3 times 2. So how does this simplify? Well, the exterior 2 times 3 is 6. And in the interior of the radical, we also have a 6. So this simplifies to 6 square roots of 6. On our slide 18, now we've got the quantity 5 square roots of 2 squared. So again, what does that mean? Well, that means we're going to have 5 times 5, 2 5s, and 2 squared. So we know the numbers on the exterior will interact with each other. So 5 times 5, that's 25, or 5 squared is 25. And then underneath the radical, we've got the 2 times 2, which is 4. And we know from before the square root of 4 has a value of 2. So this is really 25 times 2. Well, what is 25 times 2? That has to be 50. So 5 square roots of 2 squared is equal to 50. Another way we talked about an equivalent form was 25 times the square root of 4, which if you had that, that would also be acceptable at this point in time. For slide 19, we've got the quantity of 2 square root of 3 squared. So again, there's 2 sets of the insides. We're thinking about 2 times 2. And the square root of 3 times the square root of 3. So we could write it like that. And again, 2 times 2 on the exterior of your radical is 4. And then in the interior of the radical, you could have a square root of 9. So one option is 4 square roots of 9. Now, some of you might have recognized, well, if you've got 2 square roots being multiplied together, they will undo each other, right? We're squaring the square root, and we know the square root of 9 has a value of 3, so we're thinking about 4 times 3, which is 12. So we also could write this as 12. So equivalent forms of this quantity squared would be 4 square roots of 9 or 12. For slide 20, again, same idea, 2 sets of the inside. So we've got the 3 times 3. Then we've got the square root of 2 times the square root of 2. So some of you like condensing it into 1. 3 times 3 is 9. And we've got in the interior of the radical, the 4. So we could write this as 9 square roots of 4. Some of you also recognize that if you have the square root of 2 times the square root of 2, those undo each other. And so we just have 2 here. So of course, 9 times 2, that's equivalent to 18. So this quantity squared for slide 20, we could have a final answer of 18 or 9 square roots of 4. On slide 21, here we have this expression that we want to simplify. And notice in this expression, we have a couple of common items. We have a square root of 2 and a square root of 2. And if those get multiplied together, they're going to undo and be left with 2. We also have a square root of 3 and a square root of 3. When those get multiplied together, they're going to undo and we'll be left with a 3. We have a square root of 7 and a square root of 7. If we multiply those together, they'll undo and give us a 7. And last but not least, we have remaining that square root of 11. So how can we simplify this even more? Well, we're going to have to keep that square root of 11. That's the only thing within the radical, so that stays as is. Now we have these numbers on the exterior that we can multiply together. 2 times 3, that's 6. 6 times 7, that's 42. So we could simplify this as 42 times the square root of 11. For our slide 22, we have the square root of 302,436, 123 squared. The important part to remember here, when you are squaring a square root, those are inverse operations and they undo. So you will be left with what is underneath the radical. So our simplified answer should be 302,436, 123. With or without commas would be fine. Slide 23, again, we want to solve for x. So notice how you have a right triangle here. And so before, when we're doing our solving for right triangles, whenever we know two sides, to find the third, we can do Pythagorean Theorem. So our two legs are the square root of 11 and the square root of 7. So the sum of the two legs squared is equal to the hypotenuse squared. So we're going to be thinking about the following. So again, the sum of the two legs squared is equal to the hypotenuse squared. So look here, we have the square root of 11 squared. These are inverse operations and they undo, so this would be an 11. The square root of 7 squared, those are inverse operations again, so they undo and you have a 7. So now we have 11 plus 7 equals the x squared. We know we have like terms here on the left to combine, so 11 and 7, that's 18. And our job is to isolate x. So again, how do you undo something that's squared? You take the square root, and we'll have to take the square root of each side of our equation. So on the left-hand side, we've got the square root of 18. And if we take the square root of something squared, they undo, right? And so we've got our absolute value of x, which is telling us it's measuring the distance from 0. And because we're talking about a side length, we want that positive value. So our side length is going to be the square root of 18. So again, by using Pythagorean theorem, we've got our side length of the square root of 18. So that recaps today's practice on Learning Task 8.2, which built off the idea from Learning Task 8.1 that when we found the area of a square, we took the side length and squared it. If we were given the area to find the side length, we undid that by square rooting each side. So it's reinforcing the idea that squaring a square root or squaring a radical undoes each other, just like addition undoes subtraction and multiplication undoes division.